AB Calculus, section 2.5, limits at infinity. In our previous lesson, we spoke about infinite limits. So 2.4 considered infinite limits, which were referring to the behavior of a function around a vertical asymptote. In this lesson, we're going to talk about limits at infinity. So that means as x approaches infinity, what's going to happen to a function? That's referring to behavior which might result in a horizontal asymptote. So our objectives for today are to use limit notation to describe the end behavior of a function, identifying horizontal asymptotes for a polynomial, or algebraic, or rational, or trig, exponential, and logarithmic functions. We're going to use some analytical methods to calculate limits at infinity. So as we get started here, let's look at the example number 1. So let's look at y equals, or f of x equals 1 over x. We know that the function 1 over x, based on its graph, has a vertical asymptote at x equals 0 and has a horizontal asymptote at y equals 0. Using what we know about the behavior, let's use limit notation to describe the end behavior. So let's talk about the end behavior on this right side. Okay, as x goes to infinity. So the limit as x goes to infinity of the function 1 over x, we know will head toward 0. Right? So that means we can say confidently that our function will approach 0. That means there's a horizontal asymptote at y equals 0. So why would that be? Right? Let's pick a few values. Let's first graph the function 1 over x when x is greater than 0. And you can see it approaches as x approaches infinity, y approaches 0. So let's think about values. So let's look at x and f of x. So let's look at values as x gets larger. Well, if x is 1, 1 over x is 1. If x is 2, 1 over x is a half. If x is 10, 1 over x is 1/10. If x is 100, 1 over x is 1/100th. And you can see that as we trend toward infinity, 1 over x trends toward 0. Likewise, on the left side, if I were to look at the limit, maybe I don't want yellow, let's do green. As I head to the left, or as x heads to negative infinity, 1 over x will also head toward 0. Right? So if I were to, let's take the same table and flip it and make our x values negative, our y values would also be negative, but they would head toward 0 just in coming from beneath the y-axis. So you could see that 1 over x would approach 0 just coming from below. Okay, let's talk a little bit about end behavior for polynomials. Okay, so you should be able to use limit notation to also describe end behavior of each of the following types of functions, and this will apply later on, but I like to create this chart, and I like to work with positive leading coefficient, negative leading coefficient, even degree, and odd degree. Okay, so this is your leading coefficient value, is your leading coefficient positive or negative, and this is your degree. Is your degree even or odd? So as we look at the chart, if we had an even positive, right? Even positive. Well, here I find my leading term, it's 3x to the 4th. So I see a positive 3, and I see an even value for the degree, 4. So this is a positive even. That means our end behavior would head toward positive infinity as x went toward negative infinity and toward positive infinity. If we had a negative even, those two would flip, right? We'd do a vertical reflection. Okay, odd, so for example, in q of x here, we've got a negative odd. So I've got a negative leading coefficient, and I've got an odd power. Therefore, that would fit in our bottom right quadrant here, and the end behavior would look like this, up to the left and down to the right, a vertical reflection if we had a positive odd. So this tells us our end behavior. Now we can talk about the limit all day. Let's talk about the limit as x approaches, let's go negative infinity of p of x. So as we go to negative infinity for p of x, of course we said that p of x fit the positive even model. So as x goes toward negative infinity to the left, we're going to approach a positive infinity. Of course, we could say it does not exist as well if we wanted to. As x approaches a positive infinity for p of x, same is true, right? We went up to the left, up to the right. So we could say that the end behavior for p of x on both ends heads toward positive infinity. All right, q of x fit the model in the bottom right quadrant of our table here. Leading coefficient is negative for that -2, and the degree is odd with the third degree term. Therefore, we could say that the limit as x approaches negative infinity of q of x heads toward positive infinity, and the limit as x approaches positive infinity of q of x heads toward negative infinity. All right. The limit is determined by the behavior of the leading term. And the reason why is as x goes to infinity, okay, as x goes to infinity, for let's say p of x, I've got 3x to the 4th minus 6x squared plus x minus 10. The following terms become somewhat insignificant because their rate of growth is nothing in comparison to the leading term. Okay, so the leading term overpowers and overwhelms the other terms. So when looking at a rational function, for example, example 3 here, this rational function has a polynomial in the numerator and a polynomial in the denominator. Now, I want to compare this function to another function, and it's going to behave very similar as x approaches infinity. So these two will behave similarly. They will behave in a very similar fashion, but only as x increases without bound, right, as x approaches infinity. So what terms become insignificant? Well, the -7 in the numerator and the 5x in the denominator. So it's going to behave very similarly to a 3x squared over x squared. Okay, those two, let's not get this twisted, those two are not equivalent. However, they will behave very similarly. And we can see that we could reduce this to the limit as x approaches infinity of 3, which of course we know would equal 3. Therefore, what have we just done? We have identified that the function 3x squared minus 7x over x squared plus 5x has a horizontal asymptote. I'm going to abbreviate for brevity. Has a horizontal asymptote at y equals 3. Okay, so we're going to use kind of this adaptation right now in order to determine the horizontal asymptote. However, in a few examples, I'm going to show you the analytical method on how to do the same. All right, looking at this second example, let me number it 2. We'll see that this function, as x goes to infinity, will behave similarly. Okay, behave very similarly to the function. Of course, I can get rid of anything that will be insignificant in the long run. I'm going to rid myself of the 7, the x squared, and the x. Therefore, I'm going to compare this to x to the 4th over x to the 5th. Okay, as x goes to infinity of x to the 4th over x to the 5th, this would be equivalent to the limit as x approaches infinity of 1 over x. And we know that limit, right? We know that limit is 0. Therefore, the function x to the 4th plus 7 over x to the 5th plus x squared minus x has a horizontal asymptote at x, oops, not x, how about y? Yep, y equals 0. All right, for our last example, in the exact same fashion, we're going to find a comparable function as x goes to infinity, see how these trend. I'm going to drop the 1 and the 8. Those are relatively insignificant in the long run, so I'll have negative x cubed over 2x, okay, which will be equivalent to the limit as x approaches infinity of what would be negative x squared over 2. Now this limit will not have a real value. It will approach negative infinity. Therefore, the function negative x cubed plus 1 over 2x plus 8 has no horizontal asymptote because the limit as x approaches infinity does not exist. All right, let's look at the analytical method for solving and finding horizontal asymptotes with a different method here. So limits at infinity for rational functions will help determine horizontal asymptotes. That's nothing new to us. But what we want to do is we want to identify, okay, first of all, in example 4, we want to identify the highest degreed term in the denominator. So you might think, well, I see an x squared in the denominator. That's fine, okay? And that is true, but an equivalent highest degreed term is actually x, okay? What we're going to do, as you can see above, is that we're going to divide all terms by x to the nth, where n is the largest power in the denominator. So this limit is equivalent to the limit as x goes to infinity of I'm going to divide all terms by x. Okay, so I'm going to take x plus square root x squared plus 1 and x squared in the numerator and divide all of them by x. Okay, now inside a radical, I'm not dividing by x, I'm dividing by x squared because that's equivalent to dividing by x outside the radical. Thus, I'm able to then reevaluate by simplifying. So the numerator becomes x, the denominator becomes 1 plus the square root of 1 plus 1 over x squared. Okay, as x goes to infinity, what we'll see is that the numerator will approach a very, very large number, right, infinity. The denominator will approach 1 plus the square root of 1 plus 0, right? And the reason I get this 0 right here is because the limit as x approaches infinity of 1 over x squared, right, this term inside the radical, actually equals 0. Thus, I can say that the limit of the original as x goes to infinity of x squared over x plus the square root of x squared plus 1 actually does not exist, right? Because if I look at this, this will be a very, very large number over 2, which will still be a very, very large number. Okay, graphically, I'm going to look at the limit as x approaches infinity of e to the negative x. So what does e to the negative x look like? Well, here's e to the x. Let's sketch e to the x. E to the x. E to the negative x is a horizontal reflection. So as x approaches infinity, this heads to 0. Right? This heads to 0. Now, I'm going to go ahead and put my answer here, but I'm also going to analyze this in a different way. Let's take x, send it to infinity, and change e to the negative x to 1 over e to the x. Well, if I were to do a direct substitution, I would see that I get 1 over a really large number, which of course also is equal to 0. All right, let's continue with the natural log of x. So graphically, let's take a look at natural log of x. Okay, so here I've got natural log of x. Okay, it's got a vertical asymptote at x equals 0. And what you'll see is as x approaches infinity, you could be fooled into thinking that there's a horizontal asymptote somewhere, but actually the natural log of x never slows down. It just doesn't grow as fast as others. Therefore, it would head to infinity, or we could say it does not exist. Now, example 7 is very unique. Example 7 is interesting in the fact that as I substitute in directly, I would get a very large number over a very large number. So I'm thinking, right, I'm thinking of, and I'm not writing this but I'm thinking of a very, it's an indeterminate form, infinity over infinity. What that tells me is that I've got some kind of work to do. So what I'm going to do is split this up. I'm going to split it up as the limit as x goes to infinity of 5x over x plus the limit as x goes to infinity of sine x over x. Okay, now I'm going to evaluate each of these limits individually. So this would be the limit as x approaches infinity of 5 plus, now I'm going to work with the limit as x goes to infinity of sine x over x using the squeeze theorem. So I'm going to use the squeeze theorem over here. Okay, I know that this limit will equal 5, but I got to do a little work to find the other. So let's work with this. Well, I know that sine x is always between -1 and +1. So sine x over x should always be between -1 over x and +1 over x. So if I could find the limit as x approaches infinity of -1 over x, and I could find the limit as x approaches infinity of 1 over x, then I would know that the limit as x approaches infinity of sine x over x would fall right between those two. Well, the limit as x approaches infinity of -1 over x is 0, and so is that for 1 over x. Therefore, the limit as x approaches infinity of sine x over x will be between 0 and 0. Thus, this will equal 0. Therefore, our limit would evaluate to 5. Okay, please don't get this mixed up. These two limits are very different. The limit as x approaches 0 of sine x over x is equal to 1. So please pay attention to the difference between where x is headed in these two limits. Okay, let's take a look at example number 8 here. It says let f be the function given by f of x is equal to that thing. If y equals b is a horizontal asymptote to the graph of f, find the value for b. So what that's saying to us is that the limit as x approaches infinity of f of x will equal b. So let's take a look, and first let's expand f of x. So let's expand the numerator, which would be -2x squared. That will be minus 6x plus 4x, so minus 2x, and then plus 12 for the numerator. The denominator will be x squared minus 4x plus 4. So that's what f of x will equal in expanded form. Okay, so let's take the limit as x approaches infinity of said function. Now, I'm going to work this analytically. I'm going to take each of the terms of the numerator and the denominator, and I'm going to divide them by the leading term in the denominator. So the leading term in the denominator is x squared. And divide everything by x squared. Oops, so that should be an x squared. X squared. Now what I'm going to do is I'm going to reduce all terms, at least that I can, algebraically. So you'll see the leading term in the numerator will reduce to -2. The second term in the numerator will reduce to minus 2 over x. And the third term in the numerator cannot be reduced. Okay, denominator will be 1 minus 4 over x plus 4 over x squared. Now, what I want is that this limit comes out to equal b, right? So as I take the limit of the left side, what you'll notice is that the limit as x approaches infinity of -2 will still be -2. Likewise, in the denominator, the limit as x approaches infinity of 1 will still be 1. Each of these other terms, as we've talked about before, become insignificant as x approaches infinity. And the reason why is because as x increases in magnitude without bound, all of these terms go to 0 or will approach 0. Therefore, b in this case should equal -2. Okay, so using an analytical method, by dividing by the leading term in the denominator, I can see that that would be the case. Let's take a somewhat more efficient approach in example 9. It says that let f of x be the function given by that, where a is a positive constant. Find a such that the limit as x approaches infinity of f of x equals 2/9. Okay, so let's expand again, numerator, denominator. So numerator expanded will be 2x squared. Then it will be minus 10x plus 11x, which is plus 1x, and a minus 55. Okay, we divide by the denominator expanded. That'll be a squared x squared minus 8ax plus 16. Okay, now the limit as x approaches infinity of the following function f of x. Now f of x as x increases without bound will behave much like the following. Let's call this g of x. Okay, as x goes to infinity, these will behave very similarly. And the reason why is because those terms x, -55, 8ax, and 16 will become insignificant. So it'll act very similar in the long run with a similar rate of change to 2x squared over a squared x squared. Okay, if I reduce that, g of x in the long run will behave like the ratio 2 over a squared. Okay, so the limit as x approaches infinity of f of x will be equal to 2 over a squared. Now, I know that I want the limit as x approaches infinity of f of x to equal 2 over 9. So if I want that to equal 2 over 9, then 2 over a squared will equal 2 over 9. Therefore, a squared should equal 9. Now, don't make the mistake of saying that a will equal plus or minus 3. A only equals 3 because we're told that a is a positive constant. Okay, let's take a look at the last two examples here. Number 10, it says, for which of the following does the limit as x approaches infinity of f of x equals 0? So what I'm looking for is a numerator function whose limit will, as x approaches infinity, will be overpowered by the denominator. Okay, so as we look at the first example, well, you could graphically take a look at this. Right, here's the natural log of x, and the limit as x approaches infinity of ln of x actually does go to positive infinity, okay? And the limit as x approaches infinity of x to the 100th also goes to infinity. However, x to the 100th rate of change as x increases without bound is much more powerful and overwhelms ln of x. Therefore, this would head towards 0. Okay, now let's look at the second one. F of x equals e to the x over 2 ln of x. All right, so let's sketch 2 ln of x will look very similar to the red graph, except it'll stretch by a factor of 2. So again, the limit as x approaches infinity of 2 ln of x goes to positive infinity. There's no horizontal asymptote there. E to the x, an exponential function, also heads to positive infinity as x goes to positive infinity. Now e to the x definitely in this case much stronger in its magnitude and in its rate of change as x increases without bound. Therefore, this limit will not exist, right? It will go to positive infinity, or we could say doesn't exist, or we could say dne. Okay, now the question at hand is which one's more powerful, x to the 100th or e to the x? Now you might think, hey, x to the 100th grows so much quicker right away. And you're right, it does. So like 2 to the 100th, is that greater than e to the second? Yes, it is. However, over time, e to the x will overpower and overwhelm the numerator function, and therefore this will go to 0. I could use the arrow notation. In this case, I suppose I'll just use equals. Now, with regards to the pecking order of functions, your polynomial functions, x to the nth, no matter what power, kind of fall in between logarithms of base b, as well as exponentials, provided that a is greater than 1. Okay, so if a is greater than 1 and n is an integer value, positive integer to be specific, and b is greater than 1, we will have the following pecking order. Now there are a few more. You might say, well, where does the line y equals x fall? That would fall right in here. What about, for example, factorial? Factorial would be up here, and above factorial is x to the xth. Now, you will rarely, if ever, see these two, but it could happen potentially next year in your BC topics. So just kind of nice to be aware of, but I would just familiarize yourself with logs, with power functions, and with exponentials. All right, let's look at example number 11, and then that'll be it for today's lesson. So we want to find all horizontal asymptotes for the following function. Now, inferred in this problem is that there might be multiple. And in this case, whenever you see an exponential function, you should consider both ends. So I'm going to consider the left end behavior of 5 plus 2 to the x over 1 minus 2 to the x. And I'm going to consider the right end behavior of the same function. Now notice that the difference between left end behavior and right end behavior has to do with where the function is headed. So here's your left end behavior as x heads to negative infinity. Here's your right end behavior as x heads to positive infinity. All right, so let's analyze the right side first. Okay, so as we consider the limit as x approaches infinity of an exponential function, all right, let's consider that. All right, so let's sketch 2 to the x, and we'll sketch negative 2 to the x. All right, 2 to the x as x heads to infinity. So the limit as x approaches infinity of 2 to the x goes to a positive infinity. The graph of negative 2 to the x looks like such. So the limit as x approaches infinity of negative 2 to the x also goes to a very large number with negative magnitude. Okay, so the ratio of 2 to the x over negative 2 to the x would be a negative 1. They grow at the same rate of change, just in opposite directions. Now, as those numbers increase in magnitude, we'll notice that the 5 and the 1 become very insignificant. Therefore, this limit would go to negative 1. Thus, we've got a horizontal asymptote at y equals negative 1. Okay, let's look at the other end of the function, the end behavior over here on the left. Now I'm going to consult this graph yet again, and I'm going to take the limit as x approaches negative infinity of just 2 to the x. All right, so if I look at the graph of 2 to the x on the left side, you'll notice that we've got a horizontal asymptote at y equals 0. Okay, so the limit as x approaches negative infinity of 2 to the power of x actually equals 0, as well as the limit as x approaches negative infinity of negative 2 to the x is equal to 0. So as you consider the left-hand behavior, your insignificant terms actually become 2 to the x and negative 2 to the x. Thus, this limit ends up equaling 5. Therefore, we've got horizontal asymptotes at at y equals 5 and at y equals negative 1. All right, guys. I hope this went well. This is 2.5 on limits at infinity. We'll see you guys in the next video.